Okay. So just as a reminder, when we are talking about the definite integral, we are talking about area under the curve. Okay. We've spent a long time on this antiderivative concept. I want to kind of squish it together with our derivative concept. Okay, and we sort of talked about this when we introduced the notation for an integral. But I'm going to go ahead and just show you the second fundamental theorem of calculus. You can write it down, you can think about it, and then we'll talk about what it means and why it works. Okay, so this is the second fundamental theorem of calculus. Write it down. What does this mean right here? The derivative. And what does this mean right here? Okay, so Max, what happens when we take the derivative of an antiderivative? Okay, we get the function itself. Okay, so these operations are essentially undoing each other. Okay, what I want you to notice though is that our antiderivative is a function of t. But then we have our limits of integration are from a to x. So what happens is we perform the anti-differentiation. Okay, first fundamental theorem of calculus, right? Plug in x minus plug in a. But then when we take that derivative, we get back to the function itself. Okay. So what I'm going to do, I'm just going to show you how this works. So just go ahead and put your pencils down because you writing this down is not necessary. Okay. And for this purpose, capital F is going to be our antiderivative function. Okay, that's how I'm going to notate it. All right, so if we start just inside here, if we do the antiderivative of t evaluated from a to x. It has to be in terms of a different variable so that we can plug in x. Okay? Okay? So what we have is we have the derivative of f antiderivative evaluated at x minus antiderivative evaluated at a. All right? Well, what kind of value is this right here? I have a constant that I plugged into a function. What's going to come out of it? Is it going to be something with an x? Or is it going to be a number? It's going to be a number. Okay, so this is a constant right here. So this is a constant. All right, so now we're taking the derivative. Okay, so the derivative of the antiderivative goes back to our function. And then the derivative of a constant is just 0. All right, so that's how we end up with f of x. Okay, the biggest thing that I need you to be aware of, though, is that we're taking the derivative with respect to x, but x has to be in our limits of integration so that when we don't do the antiderivative, okay, right, we can kind of take that shortcut. But if we were to go the long way and do the antiderivative, then we would get that x in there. But the second fundamental theorem of calculus tells us we can just take this shortcut. Okay? Now, a does need to be a constant, so a number of some kind. So sometimes you'll see 0, sometimes you'll see -5. Okay, as long as this is a constant, that's all that matters. Okay, so we're going to do some examples, and I'll show you how things can kind of change inside of our problem. But here's our first one. Go ahead and write it down.
I just wasn't sure when
So just make sure you want to. Nope, there's one step to this problem. Okay, there's one step. The second fundamental theorem of calculus tells us that the derivative of the antiderivative is going to cancel out. So we don't have to worry about going through both or the entire process that I went through on the first slide. That was just me showing you, hey, this is going to work every time. So we know that the derivative of the antiderivative are going to undo each other. Since our limits of integration are a constant to x, we know that this is just going to be x cubed plus 1. That is literally it.
Yeah.
Okay. Next one. Okay. What is this going to be? Here's e to the x squared. All right, now, that's kind of boring, right? So let's make it a little bit more exciting. Okay, just a little bit, just a little bit. You like it boring? Okay, we still have 40 minutes left. Well, 38 minutes left in class.
practice.
So what's the point of letting it constant? Is it just there? Is it certain? Or not
No, I mean, it would if we weren't taking the derivative, right? But since we're taking the derivative, that constant's just gonna
So
go away.
okay.
Yeah, but it is important here in this example. Write this one down. And what do you notice about this problem that might be a little bit different?
Constant.
It's x to the constant instead of the constant to x. Okay? Now, does this look like verbatim the fundamental theorem of calculus? Second fundamental theorem of calculus. No, we had a to x. So what we are going to need to do, and some of you will probably just do this in your head, but I'm going to write it out. We are going to need to take the integral from 7 to x. So we're going to go ahead and flip this around, right, using our properties of integrals. So what we have is negative sine of x squared. I don't know what that was because impressive. The other way we can make these problems exciting is to do something like this. this problem that's a little different. Okay, we have x cubed as our limit of integration instead of just x. So I'll let you finish writing it down and I'll tell you what we're going to do. Okay, so we still have the same thing happening where the derivative of the integral cancels out, but since we have x cubed, two things have to happen. Number one, we plug in to our function using that limit of integration. So x cubed has to be plugged in for t instead of just x. But then also we're taking the derivative. And if we have a function inside of a function, what do we have to do with a derivative? What rule do we have to use? The chain rule. So we also need to take into account that we're taking the derivative of a composition, since x cubed is inside of our integral. So using the chain rule, we would need to multiply by x cubed derivative. So we have 3x squared times the square root of x to the 9th plus 1. Questions on that? Okay, so then I want you to write this one down, and I want you to find me the answer to this one. Find the derivative of the integral of pi over 2 3x squared cosine of x dx. I'm asking you to do the same thing. I've just written it differently, right?
Yes.
I'd like you to, at your tables, work together on that one. Well, but like my arches, like so I have really flexible arches. Like my feet are like really, like my ligaments are all really loose, so I just have to be careful. Like with my running and like wearing shoes that aren't pretty for your feet. All right, easy. What'd you get?
Cosine 3x squared times 6x.
Do you agree? For sure. Okay, so that's the second fundamental theorem of calculus. Like, that's all it is. Tomorrow we're going to go into more detail about how it relates to area under the curve. Tomorrow we'll look at, like, I'll give you a function that looks like this, okay, and the graph of e to the t squared, and we'll look at, or e to the x squared, and we'll look at the relationships with the functions itself, okay? But for now, I'm just going to have you practice taking the derivative, and we'll go into some graphical details tomorrow. The second thing that I wanted to talk about today is going back to the fundamental theorem of calculus. We're going to go and do a problem like we used to do back, like the first week we learned about integrals, okay? And then I'm going to show you how we can use the fundamental theorem of calculus to solve it a different way. They're both going to be the same amount of work, maybe one's a little shorter, but I want to talk about the benefits of being able to do it either way. So we're going back to the fundamental theorem of calculus. Go ahead and write this given information down for me, please. Okay, so let's talk about how we would do this problem with the knowledge that we had at the beginning of the semester. What's the first thing that you did? Okay, we need to find f of x by finding the antiderivative. So, f of x is the antiderivative of 4x dx. Okay, so Kinley, what would f of x be?
Sorry.
That's okay.
2x.
There we go. It's been a while, right? When we take an indefinite integral, we have to remember our plus c. We didn't have to do that on the quiz yesterday, so it's you did it on your rules quiz, but that's really been it for a while. Okay. Then, if we know that f of 0 is 6, we can use that to find c. So we know that when we plug in 0, f of x is 6. So what is c? Okay. So we know our function f needs to be 2x squared plus 6. Oh, what am I looking for? F of 3. So to find f of 3, what do we get? I would say that's not a very strenuous problem. I don't even think it's really that tedious, but we could do all of these calculations without having to find the plus c. It would still involve us doing the antiderivative. It would still involve us using 0 and 3 and plugging them in, but we would not have to find that plus c in order to figure out what f of 3 is. Okay? So let's talk about the fundamental theorem of calculus, okay? And I'm going to write it a little bit differently than you wrote it in your notes, right? But we talked about how the integral from a to b of f prime of x dx, and I'm using f prime because I think it fits better with our example. But what's the antiderivative of f prime? F. So we know that this is f of b minus f of a. That was our fundamental theorem of calculus. Do you agree? Okay. So what we can do with that piece of knowledge then is we can say, all right, well, we know that the integral from 0 to 3 of 4x dx is f of 3 minus f of 0. Okay. Where did the 0 and 3 come from? Those are the x values that they give me. I know f of 0, which is why I'm using it. I'm looking for f of 3, which is why I have it in my integral. So we can come over here, and we know that f of 0 is 6. And then we know how to do this over here. This is 2x squared evaluated from 0 to 3. So we have 2 times 3 squared minus 2 times 0 squared equals f of 3 minus 6. So we can conclude that f of 3 is 24. Okay. First of all, do you have any questions about how I set it up, why I set it up the way that I did, or any of the steps along the way? Okay. Do you feel that this is more efficient, less efficient, excuse me, less efficient, or about the same? Some of you say same, some of you say less efficient. Yeah. I took up less room. Okay, this wasn't actually part of my work right here. This is my work right there. Okay, now regardless, like it really doesn't matter in this case how you feel about it, okay? Because you could do either way. But if I were to give you a function like x sine of x, we have no way to integrate that with the tools that you know right now, okay? You do not know how to integrate this until you get to calculus 2, okay? So if this were the case, we would have to use our calculator to do any of our calculations, okay? And this is why I want to teach it to you without a calculator, so just so we have more practice. But you're going to come across problems over and over, especially when we do our AP work, where we have to use this fundamental theorem of calculus in order to find a function value, because the only way to integrate is with our calculator. If we cannot integrate by hand, then there is no way for us to come over here and find a plus c. Okay? But if we can use our calculator, then we can come over here, we can put this into our calculator and then add over whatever we need. Okay? I want you to be able to do it without a calculator first before we get the calculator thrown in there, which is why I'm using basic examples. But that is where we're headed with this. So let's try one more. Go ahead and write this down, and I want you to set it up and work through it together at your table. We'll go through it as a class, but I want you to try on your own with your peers first. Please use the fundamental theorem of calculus way. So the second way that we did up on the board, that's what I want you to use right now. Okay? Hearing the buzz of a number 24. Is that through? No. Just 24. I did not mean for that to happen at all. So 24 is a nice number. Mm-hmm.
The only reason it's a nice number. I thought it was 7.
7 is,
Oh, it's just,
that is also.
I feel like so many people like that number. Yeah. It's just like, it's not even. It's like,
But people also are attracted to prime numbers also. You know what I mean? Like 3, 7, 13. Like those are awesome numbers. Like that. Okay, so as I've been walking around, we should have negative 1 to 2 of 6x minus 8x cubed dx equals f of 2 minus f of negative 1. Okay, so what's our antiderivative here? 3x squared? minus 2x to the fourth. Okay. Evaluated from -1 to 2 equals 3 minus f of -1. What do you get for your definite integral over here? What? -21. Okay, so we have to subtract the 3, but then this is negative, so we have f of -1 is 24. Okay, so I don't think that your homework is going to be overly strenuous today, but it is coming from 2 different places. Okay, so I'll let you get a head start to it. I have a worksheet with 7 questions. The first 4 are asking you to do, basically I don't give you find f of 3, I'm just asking you to find me the function, like so basically solve for c, okay? But then the last 3, I actually ask you for a function value, and I am asking you specifically to use the fundamental theorem of calculus to do it. Do it this second way just so you get the practice and can recognize when we can do it later on down the road, okay? Then you also have like 6 problems from your book, okay? Whether you want to do those on the back of this worksheet or in your notebook, I don't really care, but those both need to be done before tomorrow. So if you want to take these next 14 minutes and get one of the 2 pieces to your assignment started, maybe either completed, go for it. Maybe you can do your book work right now, that way you don't have to worry about your book this evening. Since there's only 6 problems, I bet you can get them done in this time. Yes, you can.
Did you give anyone else